Okay, so it's 2 past 1 now, so let's get started with this. It looks like everybody's muted, so that's great. Feel free to interrupt me with questions. You can unmute yourself and ask a question, or you can type it in the chat. I'll be looking at the chat more occasionally. It's a bit hard to look at two screens at the same time, though. So, but I'll catch most questions, and I'll make sure to answer them all. Okay, so oh yeah, one note. This session it will be recorded. So if anybody has any objections, let me know, and I'll make sure you get cut out and that you don't appear in the video when it gets posted on our website. Yeah. So GPU programming. GPU programming has been around for quite a while, and it's a really good technique to handle certain problems in a massively parallel way. So you can get massive speed boosts, but it depends on the problem. You need something that can be adapted for the GPU. So that's just something we'll talk about in the seminar. I have a link with the code. So at bitbucket.org/Dr. Jarno/GPU, and that's your SRC stands for source. It's optional, but it gets you straight to the code. All the code examples that I'll be talking about today will be available there. And also I'll send out the slides afterwards, and the video will be recorded probably next week or maybe the week after that. Yeah, so what's the difference between a GPU and a CPU? GPUs are really good at handling very many simple tasks at the same time. So they have many more cores. If you look at a typical GPU, they have thousands of cores on them versus a CPU which only has tens. I think the AMD Threadripper is one of the biggest one these days, and they go up to what is it, 48 or something. But if you use GPUs, you get a lot more processors. They're less complex though than CPUs. And what I mean with that is they have less specialized instructions that the compiler can use to optimize your code. They also have a slower clock speed than CPUs by about a factor of 4 roughly. And they also have less memory. So for problems you need to tackle with the GPU, you need to have something that you can split up in a lot of small tasks, and that's really where GPUs shine. And it makes sense because GPUs, they're meant for graphics acceleration. So the thing that they were designed for was taking a big image with lots of pixels and then do an operation on each of those pixels. So you need something that can handle a lot of small tasks quickly. And the calculations are done by something called a kernel. So a kernel is a small program that you compile for that specific GPU, and then that little program will work on each element of an array simultaneously. So you have basically two programs running at the same time. You have the program that runs on your CPU, and you have your program that runs on the GPU. So the way that works is like this. So first you initialize everything, and then you allocate memory on the CPU. So the left side here is CPU, and on the right I have GPU. So you allocate memory on the CPU for your calculations, but you also allocate memory on the GPU. And these are separate devices, so they can't talk easily with each other. It always has to communicate through some code on the host on the CPU side. So once you allocate memory on the host program, the CPU part of it, you fill that with input, and then you send that over the bus in your computer to the GPU, and then the GPU has that kernel that it runs on that input. It gets results. The results are on the GPU, so that needs to be copied back to the CPU side, the host program. And then finally you're done, and you free the memory on both sides of the program. So yeah, it's like a program, but it's more like two programs that run almost independently of each other. And then there's a bit about GPU architecture. So I mentioned there are thousands and thousands of cores in a GPU, and the way it works is you have all these little purple squares, and they represent threads. So each thread will work on, well, one pixel if you're doing graphical calculations, but one data object. So each purple block here will work on one data object. And these threads is what they're called. They are organized in what is called blocks. So one block has can run multiple threads at the same time, and they are separated out like this. So for modern GPUs, I think the number of threads is around 1024 or 2048. It depends on how expensive your GPU is. And also they have access to a shared memory. And we'll get back to it later. But shared memory is something that you can access really quickly. So if you have threads in the same block, they can communicate with each other fairly quickly. If you have threads in different blocks, it takes a bit longer. And that's important, and we'll get back to that later when we get more into the nitty-gritty details. And then there are different platforms. So one of the most popular ones is CUDA. You may also have heard of OpenCL. And both are programming languages that can be used for GPU programming. There are a few major differences. So CUDA, it's only available for NVIDIA cards. So if you have an AMD video card or an Intel video card, then you will not be able to use CUDA. However, OpenCL, it runs on everything. It can even run on CPUs. So that it can run on CPUs is quite nice actually, because you can always run your program anywhere, basically, even if there's no GPU available. And due to the way OpenCL works, you can actually still get a speed boost. Yeah, and CUDA is proprietary, and OpenCL is open source. It's nice because you can see everything that's going on. CUDA is also very fast because NVIDIA really makes a big effort to make sure that they stay on top for the GPU computing market. OpenCL is also very fast, and in some areas they're less fast. It's a bit hard to compare because it really depends on what you're trying to solve. And then for CUDA, you need a GPU if you want to develop the code. So you need to have access to a machine that has NVIDIA cards in it. Otherwise, you can't even test your program to run. With OpenCL, you don't need the GPU because, like I mentioned before, you can run on the CPU. So you can try all your programs on your own computer. And then when you're comfortable with it, you can send it out to a cluster or something that does have a GPU. And then finally, CUDA, it has very good documentation. If you go to their website, there's tutorials, there's really good manuals, all of that. OpenCL is not that great. they they have some documentation, but it's hard to find examples. Part of that is because CUDA is much more popular than OpenCL. So in this workshop, I'll touch briefly on how to program in OpenCL, just so you can see how it works. But the bulk of the talk will be about CUDA, simply because that's used the most. So to get started with CUDA or OpenCL, you need to download the software for it. So I've put the links in this slide. So for CUDA, you can go to the NVIDIA website. For OpenCL, depending on what card you have in your computer, you can get the Intel version, AMD version, or NVIDIA version. You can actually install multiple at the same time. OpenCL doesn't really care. If you have both of them, then it will just choose whatever you tell it to use. So that's kind of nice, actually. So with that out of the way, we can see a bit on how GPU programming works in more detail. So in the beginning, I mentioned that you need a kernel for the GPU side of things, and that does the actual calculation. So what I put up here is an example of what such a program could look like, and they're typically quite small. So the way it works is, this is OpenCL, by the way. So you write it in in C. So void kernel, and then the name of your function, and then the parameters that you want to work on. And then you have, in this case, it adds two vectors. So we have a vector A, and we have a vector B. And we want to add the content of vector A and vector B and get a vector C. So C will contain the sum of A and B. So that's what happened in the next line. So get global ID 0, that gets the index in the memory of the current thread. So C of this element is the sum of A plus B. And you'll notice that there's no for loop here. So this really only works on one data item. But this kernel add, it's executed by all of the threads at the same time. So that's a bit a weird concept. I mean, I would expect a for loop here because you have to loop over all the elements in your vectors. But the kernel already iterates over all the elements in your memory, so you don't have to do that anymore. And you just have to get the ID of the current memory location you're working on. So all the threads are doing this at the same time. And then for compiling, this is for Linux and Mac. For Windows, you would probably use something like Visual Studio or whatever. And in that case, you need to make sure that you include the OpenCL library, and the rest is the same thing. So I have an example program for that. Let me just open it up. So this is what a typical small program looks like in OpenCL. You have your kernel add program, and that's the code I just showed in the slide. So this is the add of the kernel. And you'll notice that I define it as a string. You can also save it into a text file and then load the text file in your code and feed that to OpenCL. Okay. And then we have our main function. Oh, by the way, I forgot to mention this. The coding examples, they'll all be in C and C++. You can also use Python using the libraries that are available. So basically any programming languages that supports CUDA, the idea is the same. I'll just be using C because that's what I'm most familiar with. It's also faster than Python. So I'll use C and C++ as my examples. But the general IDs, they will work for anything. Yeah, so the first step we need to do is to open the context. So the context, it tells the program what is available. So what tools you've installed, like the Intel tools or the AMD tools or the NVIDIA tools. And it also tells the program what devices are available, like CPUs or GPUs. And if you have multiple GPUs, you can also select which one you want. For this program, I will go with CL device type default. And sorry, and that will just pick the first platform, the first device. It will just take whatever it finds. So with CL device default, it just picks the first capable device that it can find. And then we have the very last argument is contains the error. So if it couldn't find any software or any devices, it will give you an error. And CL success is if everything worked all right. So this is just the error code function. If something fails, it will stop the program and it'll tell you why. Now, suppose that worked. You got your kernel and it worked. Then you need to load and compile the kernel. So the kernel is now defined in the C++ program, but you need to compile it for that specific device and move it towards the device. So in our case, it's going to be an NVIDIA kernel. Oh, I saw a question from Fabrizio, why 0? Let's see, so that's this 0 here. That is because you can define its indices in a multidimensional way. So depending on what your problem looks like, you can address the memory as a 1D array, a 2D array, or a 3D array. And here we're only using 1D arrays, so we're only using the 0th dimension, and we won't bother with 1 and 2. But yeah, if you have a problem that uses a 2D memory, then you would have 0 and 1. And for 3D, you would have 0, 1, and 2, etc. So yeah. So the first thing to do is, the second thing to do after you have successfully loaded the context and you know what devices are available, is to compile the kernel. So kernel add program, that's the string that we have here at the top. So that's our kernel program. We put that in sources, and then we make a program that uses those sources on that context that we defined earlier, and then we build it. So in OpenCL, you actually compile your program when you run it, and it gets compiled for that specific CPU or GPU device. And then, and then if it fails, so if it's not CL success, it says failed to build, and it will tell you why. So now your kernel has been compiled. You know what devices you have. So then you can move on to handling the data. Here we have 40,000 numbers that we want to add. So we create a buffer. A buffer is a memory location that exists either on the CPU or the GPU, and it will contain the memory that you transfer back and forth between the two. So here we have a read-only memory, another read-only memory, and this is from the point of view of the GPU. And then we have write-only. So the reason for that is that we use A and B and store the result in C. So we read A, we read B, and we store in C. So we write to C. So that's the buffer. Now you need to actually allocate the memory in your host program. So you have your new float and your numbers, and same for A and B, and then you fill it with some initial values. So here I fill it with some values like a quarter I and 3/4 I. So if you add that up together, you would get I. So that lets me quickly see the result is correct. So now we have the memory on our host program, and we have defined what and where the memory is going to be used on the GPU. And now we also need a command queue. And the command queue is used for sending commands towards the GPU. So these commands could be send the memory to the GPU, or get the memory for the GPU, or run this particular program on that memory. So the queue is what we need to communicate with the GPU. So the first thing we do is we send the data from this host program. So we've defined over here A and B, it contains data in the host program on the CPU. So we have this buffer that is responsible for the communication of buffer A between the CPU and the GPU. So CL true, it means blocking. So that means that this command will wait until the operation is completed. It's not the fastest way to do things, but it's the safest way to do things. So when you're just starting out, I would recommend keeping that for true. 0 is the offset, so where in the memory location you want to start. So we'll just keep that 0. And then we take the number of bytes in A, and we send A to buffer A. So once this command is completed, that means that the memory content for A on the CPU side has been transferred to the memory content of buffer A on the GPU side. And we do the same thing for buffer B. And now that the memory has transferred from the host, from the CPU to the GPU, we don't actually need it in the CPU side anymore. So we can just delete it. So now we have data on the GPU. and we're ready to start our calculations on it. So to do that, we have to run the kernel. And so you define the kernel. I call kernel add because it's a program that will add. And then I set the arguments, so buffer A, buffer B, and buffer C. And if you look back up, that corresponds to the first argument, the second argument, and the third argument. So that's set argument 0, set argument 1, set argument 2. So now we have the program we want to run and the arguments that we want to give to that function. And then we enqueue the kernel. So we set this kernel in the queue as a calculation that the GPU needs to perform. So this second argument, it lets you specify the dimensions and the layout and all that, but we'll use the default things, which corresponds to null range. So that means we just let OpenCL figure it out for their own and just use the default values. If you're going to do a bit more advanced stuff, you might want to tweak this, but for the purpose of this seminar, I'll just keep it as simple as possible. So we'll keep null range for the default values. The only thing we need to say is how many numbers we want to use. So that's what you do with ND range. So it gives you the range of numbers that needs to be processed so that the kernel, so that the GPU knows where and until where the data starts. And then finally, when that is done, we need to get the data out. So we allocate some memory on the CPU side to store the results of the GPU memory. So we create C, so new float with numbers, and then we enqueue read buffer. So we're asking the GPU to please send the data that it has in buffer C, which was the write-only memory that we defined earlier. The CL true is again this blocking, so you'll be sure that the memory has been copied if this function returns, and then how much you want, and it goes into C. So now C contains the sum of A and B, and then you can show here the results. So I have that over here. This is OpenCL add. So there I have my program add.cpp. Let's just make that a bit bigger. That's my program add.cpp. So I want to compile that. So I compile it, add.cpp, and I want to call the program add, and I need to use OpenCL. So it's giving me a warning because my code is kind of old and there's already OpenCL 2.0. I'm still using 1.0, so that's why it's giving me this warning. But it did create a program, so I have add here. And then if I run that, it gives me the output, which is the sum of A and B. And if I look back in the program, I had defined A as a quarter I, B as 3/4 I, so the result should be I. So that's just the index of the number. So if I go back to the output, you can see it just adds up until it gets to 40,000. Well, it's 0 to 40,000, so this was 40,000 iterations. So that is the simplest GPU program you can make. And that's what's with OpenCL. We can do the same thing for CUDA. And you'll notice that the notation is a tiny bit different. So we have global, void add, and then we have our arguments again. And now it's called thread IDX X. So that comes back to the dimensions where you can use X and the Y and the Z axis. But that ID is the same. So again, there's no for loop. So every thread works on its own little data thingy, and which is pointed to with index. And compiling is done with NVCC, which is the NVIDIA compiler. And it creates a program just in the same way. So let's open that one. Let's go back to CUDA add. So you notice it's add.cu, so that means CUDA program. Let's make that bigger. So yeah, here's our function. So we have global. That means that this is a kernel function. You also notice this is different from OpenCL where we had defined this as a string. CUDA actually compiles the program immediately. And it's not passed as a string, it's passed as an actual function, which is nice because then when you compile the program and you made a syntax error in here, it will tell you immediately. Whereas with OpenCL, it will only compile on runtime, so then it's too late, basically. So here you also get, yeah, so this uses stride. Probably shouldn't have put that in there, but it's a way of working on the data in such a way that a thread can work on multiple data points one after another. You can just ignore that for now. The important thing is that it's CI, AI, BI. It's going to add A and B, store the result in C for every thread on the GPU. Then we have the same thing, numbers, floats. CUDA has something called managed memory, and it's something that OpenCL doesn't have. And it's nice because you can have the memory on both the CPU and GPU, and you only need to call one synchronize function, and it makes sure that the memory is in sync between, so that the memory is in sync between the host and the GPU. So you use CUDA malloc managed. In A, I want to have this many bytes, and the same for B, and the same for C. And of course, we always need to check our errors to see if it works, because if you ask for too much memory on the GPU, it will fail, and you need to check for that. Then we have the same initialization routine as before, so a quarter I and 3/4 I, so the total should be I. And now this is how you run the kernel in CUDA. So add, which is the name of our function, our kernel function that we compiled with it. And then we use triple smaller than, and triple larger than symbols. And the first number is the number of blocks. So if you remember, we had blocks on our GPU which contain threads. And then the second one is the number of threads per block. And then we give our arguments, so the number of numbers, A, B, C, which corresponds to the add function N, A, B, C. Yep. So then we call the function CUDA device synchronize. So it will transfer the memory for you because it's managed memory, and then it will run the kernel for you, and then wait until it's done. And then when it's done, it will output the result in the exact same way. So you can see CUDA is more user-friendly. It's much less verbose. It's probably also a reason why it's so popular because it's much nicer than OpenCL. But the big downside is that it only works for NVIDIA. So let's go to, let's see, CUDA add. So we have our source code here at CU, which you can compile with the NVIDIA compiler. .cu, and I want to call the program add. And now it's done compiling, so let's see. Now we have our executable add here, and we can run it, and we'll get the same result as we did for the OpenCL program, because they are doing the exact same thing. So now you have the skeleton for making a CUDA program. And you can imagine that you can start building it from here. You can make it as complex as you want, of course. So I did that. And there's one thing also about CUDA. It's something called warps. You don't need to know too much about it. I only bring it up because it can affect your efficiency of your program. So each block has a number of warps. So inside the block, there's another substructure that works kind of like a multi-core processor, and it has 32 cores per warp, and then there's so many warps per block, and then there's so many blocks per GPU. And the only thing I want you to take away from that is that if you want to program things efficiently in the GPU, you should make sure that the number of threads is a multiple of 32, because then everything fits in nicely and it's the most efficient for NVIDIA GPUs. It's usually 32. It can be different depending on the GPU use, but if you use 32, you're probably okay. So that was all about how you run the program. And the thing about GPU programming though is a lot of accounting. And by that I mean where the memory is, what memory you're using at the moment, which is the fast memory, which is the slow memory, etc. So this diagram aims to show that. So we have our host program on the left here, and that's your C++ or CU program. And it communicates with GPU through either CUDA malloc or the buffers that we had in OpenCL. And when you send data from the host to the GPU, it gets into what's called the global memory of the GPU. So this is the big memory. When you buy a GPU and it says it's a 24 gigabyte card or 32 gigabyte card, and it's referring to this global memory. And each thread inside of a block can communicate with that global memory. So if you remember the code, it had something like a thread index, and that points to the global memory. Then each thread also has access to a register. So if you type something like int a inside of a kernel, that will be inside of the register. So the register is very small. It's per thread, but it's extremely small. It's extremely fast, sorry. So if you want something to be fast, you want to use the register. There's also shared memory, and each block has its own shared memory. It's about a factor of 100 faster than the global memory. So if you can get away with using shared memory, that would give you a big speed boost. However, shared memory is limited to a block. So threads inside of it have access to the shared memory. But if you want to access the data from like another data element that's in a different block, then you need to go through the global memory, which is slow. So global memory is slow. Well, it's not really slow compared to the other ones. Global memory is slow, then shared memory is faster, and register is the fastest. But register is only available to thread, shared memory is only available to block, whereas global memory is available to the entire GPU. And the key about making efficient programs is making sure that you use the memory efficient. And I'll show you a sample program for that later. So yeah, what we've learned so far is what kernels are and how to use them. I've also shown you how to move memory, and I've told you which memories there are and which frameworks there are, so CUDA or OpenCL. Let's see, was there a question? Is there a reason for using OpenCL on a CPU? Yes, actually. So the way OpenCL works, it changes the underlying algorithms. So I'm not entirely sure how they do it because this goes beyond me, but it's actually possible to write an OpenCL program that runs faster on a CPU than if you were to write the equivalent CPU program. Just because of the way it's so massively parallelized and so efficient that it can do a lot at the same time. So it's using probably the special instructions in CPUs that you would normally have to aim specifically to take advantage of. And OpenCL does that for you. And also the other advantage is that you can program on a laptop or a computer that does not have a GPU, test your programs there, and then when it works, you send it off to a big computer that does have a GPU. Okay, so that was all the questions. Let's just take some water here. So Now I'm going to show you a bigger program that uses all this memory. So it uses the register, it uses the shared memory, and it uses the global memory. And it tries to do that in an efficient way. And the simulation I'm going to do is particle dynamics. So this is a particle simulation. These particles, they attract and repel. And this is always a gamble if it works over Teams or not. But if you play the video, you can see that they start attracting each other and repelling each other. So the function I wrote is that if they're far away, they attract. If they're close by, they repel. And there's like a zone in between where they don't do anything. So you get this nice sphere structure where the particles are trying to get as close to each other as they can, but they don't want to be too close to the other particles. So you get this nice sphere structure, and the, it's actually a sphere that's filled entirely inside as well. And it also looks pretty, at least I think. So we're going to do an n-body simulation, and we're going to use n threads for n particles. Forget how many particles I used for this. That was probably like 1,000 or something. Anyway, so each particle has to interact with every other particle. So for every particle, I have to look at n minus 1 particles and calculate the force between them and do that for every particle. So it's n times n minus 1. So this is an n squared algorithm. You can make this more efficient. You can box them, and then you can calculate the force inside of the whole block and compare it to the others. So you can actually bring this down to n log n, if I'm not wrong. But for simplicity, I'll just use this brute force one. It's an n squared algorithm, and it runs just fine on my GPU. And actually, the GPU I'm using is for probably 8-year-old laptop, so that's pretty impressive. So, oh, sorry, this is only going to be CUDA. So I'm stop using OpenCL. I just want to show you that OpenCL exists and that you can use it. But because CUDA is the most popular one, I will concentrate on that one because it's the most likely that you'll be using that anyway. Yeah, so there is a statement called device, and device is used to define functions that can be called by your kernel. So these only exist on the GPU. You cannot call them from the host program. So it's an example for the distance between two particles. Actually, the distance square, which is by distance 2. And I use a distance square so I don't have to take the square root, which is an expensive operation. And it calculates the distance between two particles. So float 3 is a data type in CUDA. It contains x, y, and z, so that it indicates the three-dimensional position. Then r is the distance between those two particles. So the difference between the difference between the x coordinates, the difference between the y coordinates, difference between the z coordinates, and then I calculate the square magnitude of that vector, and that's what I return. So this is a function that calculates a distance that exists only on the GPU and can be called from your kernel. And we have another function that does something similar for the force. It uses the distance function and it calculates the force from one particle on the other particle. So if you want to have a function that's both callable from the host program and the GPU program, you can use host device, and then that function will exist in both, which is useful for testing because then you can call that function from the host. You can see if it works, and then you know if it works. It also works for the kernel. And then we have the memory. So that's the same as before. We use malloc managed. So that means that CUDA will take care of syncing the memory between the GPU and the host program. So we have our particles and we have our velocities. And now it's size of float 3 because we use three-dimensional vectors for indicating the particle positions and the particle velocities. So then we initialize that on the host and we sync it to the GPU. So we give all the particles random positions with this random number generator, and we set the particle velocities to 0 for all the particles. So all the particles start at nothing. I start the simulation and they start attracting and repelling each other. And then I synchronize to get the memory from GPU, from the host to the GPU. And then we have our kernel function. So our kernel function has quite a number of arguments. There's a number of particles, a number of iterations, and then a coefficient for the force. And I also put in damping so that the particles can come to rest. And then we have the memory for the particles and the velocity. And now, because we use multiple blocks, before we were only using threads, but now we want to use all the blocks, we have to get the ID in the memory using this formula here. So the block ID, so that's in which block of the GPU you're using, times how big that block is, times the thread ID. And I'll show you a picture later to make that more visual. But suffice to say that GID points to a location in the data for a specific thread. Then I loop over all the other sorry. Then I loop over other sorry. Then I loop over the other particles, and this code is still run for just one thread. So each thread runs this code. So if my position, that is the particle that corresponds to this particular thread, you can see the GID, which is the index for this particular thread. And I start with my acceleration, which I set to 0. And then I go over all the other particles, excluding myself, and I calculate the force between the other particle and the particle for this thread. And I put in the coefficient, which determines how strong the force is. And that gets me an acceleration. And that's what I add to the acceleration of my particle, which is the particle for this particular thread. So every other particle, so this is my particle, and every other particle will calculate, sorry, for every other particle we'll calculate the force, and that will determine the total acceleration for that particular particle, basically using Newton's law. Then I sync the threads, so I make sure that the acceleration has been calculated for all the particles. So sync thread will wait until all the threads on the GPU have reached the same line in the code. And that's necessary because now I'm going to update the positions of the particle. And I don't want to update the positions of the particle while I'm still using that to calculate acceleration. So we need to make sure everything is sync. The acceleration has been calculated for each particle. And then we can use that to calculate where the particle should go. So the position, I'm putting a damper coefficient and after my previous velocity, and I add acceleration to that as well. And then I update, then I update the velocities and the particles based on what my acceleration was. And I do the same for the y and the z coordinates. I'll go over this code in more detail. And then we call the kernel, which is also something we've done before. So now we have a kernel that has defined instructions on what to do with the data. And then we call it. So we have the number of blocks and the block size. So the block size is the number of threads you have available in a single block. And these are all the arguments that we give to the kernel function called iterate. And you'll notice again the triple smaller than and larger than, which is CUDA specific. And then we synchronize again. So we wait for the GPU to do all the work. And then we write the particles to a file from the host program, from the CPU side. And yeah, you need to make sure that the number of blocks times the block size is the same as the number of particles. So, well, then we're done. But faster would be nice. And the way to make it faster is if you use a shared memory, because now we've been using global memory and we have not been using any of the other memory. sorry, we have not been using the shared memory. So that's the memory that is available per block. So I'll go back to the memory layout. So what I mean by that is um, I want to use a shared memory. And if you send the particles to the GPU, each thread will be in a block. So we have a block size of 1024 here. So there will be 1024 particles in this block, 1024 particles on this block, and we can make those particles interact with each other. But we cannot make them interact with particles in the other block if we use shared memory, because for that we have to use through global memory. So we have to do we have to use a specific algorithm that optimizes for using shared memory, and that's possible, fortunately. So the problem is how to get particles on block 1 to communicate with particles on block 2. So with particles in block 1 and particles in block 2. And the answer is that you can communicate through the global memory, but still use as many calculations on the shared memory as possible. And the algorithm that we'll use for that is called the multi-tell algorithm. And that's where you load, actually, I think my next slide says what that does. No, it doesn't. Okay, so where did it go? There. Um, so the way that works is you calculate um, the force between all the particles in the shared memory. Then from the global memory, you copy all the data for the next batch of 1024. You put it in, then you calculate, and you keep repeating that. It sounds a bit fake right now, but I will go through the code and do it step by step by you. But the reason it's called multi-tell algorithm is because you take 1024 particles at a time and calculate based on that. So that to be able to do that, we need to know what the block size is. And there's a CUDA function called CUDA defines get attributes. And that allows you to query the GPU and get its get its properties. So in this case, we want to know the max block's dimension in the X because we only use one dimensional. And that is going to be stored in block size. So we actually ask the GPU how big should our blocks be? How big are your blocks? And then we can optimize for that. And to use shared memory, we need to change our kernel call. So before we had iterate and smaller than, smaller than, smaller than, num-blocks and block size. And that's all we had. But now we're going to use shared memory. We also have to give it a third parameter called shared memory size. And that's how much of the shared memory you would like to use per block. And the calculation for that is the number of particles divided by the number of blocks times the size of the float 3. So that's the particles are divided over all of the blocks. And you have so many particles per block. And that's the amount of shared memory that we want to use. And then to access that in the kernel function, you have to define something called extern shared float free. So shared gives you tells the compiler that this corresponds to shared memory. And local particles, you'll notice that there's nothing here. It gets its size from the argument you put in your kernel function here. And there's only one external shared. If you want to have more data structures, you have to define it yourself. So then you have to put in numbers. So suppose I say shared memory size is, I don't know, 2000. And we want to have local particles and local velocities. So I could do local particles 500, local velocities 500 for a total of 1000. Wait, I just said 2000. Anyway, you should make sure it adds up. So here's the multi-tile algorithm. I copy the particles in block 1 to the shared memory of all the blocks. So I take the first 1024 particles and I copy that information to block 1, block 2, block 3, etc. So each block in its shared memory will have the first 1024 particles. And then I calculate the force between current particle. So current particle corresponds to one thread inside of that block. And it calculates that force between that particle in that block, in that thread, to the particles that are currently in the shared memory. And then you add that acceleration to your current particle. And then when you've done that, you know the force of your current particle in that thread to the first 1024 particles of all of the particles. And then you copy the second block of particles. So we take the particles in block 2, we copy that to the shared memory of all the blocks. So this is the next 1024. And then we do the same thing. And we add that to the acceleration that we already had. And then we do it again for the next one and towards the next one. So shared memory, the first iteration, this will have the first 1024 particles. This second block will also have all the first 1024 particles, and the next one, etc. as well. And then when you're done with that, you load from global memory the second one into shared, and the second the second batch of 1024 particles in the shared memory. So yeah, it's a bit of a tricky algorithm to get your head around. So I would heavily suggest you look at the code afterwards and try to make it work yourself, because that's really the best way to learn. So I'll open the CUDA N-body program now. Let's see, CUDA N-body. So this is the distance function that I mentioned in the beginning. It calculates a vector that is the distance between that points from one vector. Sorry, it's a vector that points from particle 1 to particle 2, and it's a difference vector, so x minus x, y minus y, etc. And it calculates the distance or the magnitude squared. And then I have my force function, so it takes the function distance2, which is this one, and you'll notice that it's a divides function, so it only exists on the GPU. So I get my first particle, my other particle, and then the force, which is what I'm going to return. If the particles are closer than 10, so 10 squared is 100, so distance 2 gives you the distance squared, then I want to repel with a certain coefficient, and it's the force is proportional to 1 over the distance, I think, because this is, yeah, so this is the distance in the x direction divided by the distance squared, so this is a 1 over r force, so like sound or whatever. Not sound, but you know. And if they're further away from each other, then I will attract. So particles far away will attract, particles close by will repel. And if they're anywhere in between, I just don't have any force whatsoever. So they just drift. Then I have my kernel function, which you can see because of the global keyword. And my iterate, these are all the arguments that I give to the iterate call in my main, which we'll get to down there. Then I have my shared memory, so extern shared, which gives me access to the shared memory on that block. Then this is the thread index inside of the block. So that corresponds to the index inside of the shared data. So the shared data, it's the memory inside of a block. And the thread index is the index of a thread inside of the block. So you can see that that corresponds. Then we have the global ID. For the global ID, you need to take into account the block index times the size of the block plus the thread ID. And that gets you the memory in that gets you the location in the global memory. So I do about 20 iterations in the GPU side for every time we call the iterate function. And that's just a way of keeping things on the GPU, because the more you keep on the GPU, the faster it is. You don't want to switch back between the host and the GPU all the time. So I think I set this to 20. So I do 20 iterations inside of the GPU before I return to the host to write out the data and then do it again. So my position is the global ID. So that is the particle that corresponds to a thread inside of the block. So every particle is going to have calculations done on it for it simultaneously. And I start with 0 acceleration. Then I need to copy the memory from the to the shared memory of the first 1024 particles. So I take the 1024 particles, and for each, yeah, ignore the for loop for a while, for now, and this part is the important part. So the local particles, no, that's not the question. Okay, so the local particles is the shared memory. So this is the index towards the shared memory, and then I take the particles, which is, well, this is the thread index and the block index. But this happens for all the particles at the same time. So for every block, I take the 0th particle, and then for every block, I take the second particle, third particle, etc. And I all copy them to the first 1000. I'll copy the first 1024 particles to the shared memory for all the blocks. And then I have to wait until all the threads have copied the data before I can do anything with it. And then I calculate the particles for my particle versus all the particles in the shared memory. And I don't want to do myself because then I'll be dividing by 0, and you don't want to do that. So I calculate the force, I add it to the acceleration, and then when I'm done with all my 1024 particles, I wait until all the threads are done. So at this point, I've processed the force due to the first 1024 particles on all of the particles. So then I know the acceleration, and I can update my position, and sorry, I can update my velocity, and I can update my position. But then we have the other particles. So we go back to the for loop, and then we do the next block. So this loops over the number of blocks. So now we do the next block. Again, we store the next 1024 particles. So that's particle 1025 to particle 2048. We store that in the local particles in the shared memory, and then we do the same thing. So we calculate the force due to the next 1024 particles on all the particles. So all the particles get updated again with the forces from uh, the current block of particles. And then we do that for all the blocks. So at the end, we'll have done all the particles and we're done. And then finally, I save my velocity. So that's the velocity after all these calculations have been done. I save that in the data velocities at the particle at the index for the current particle, the current thread. And if you remember, that's up here. There. It's the last argument. So that is stored in the GPU memory. And then later we'll read that GPU memory towards the host program so we can write it to a file. So here we have a function for writing the particles, which is not very interesting. So you'll notice that there is no a global or no device. So that means that this is a function that's defined on the host side. So this is something that your CPU program will be calling. And all it does is it takes the memory of the particles positions and the velocities, and it outputs it. Let's see if a question. What is the parameter velocities? So the velocities, it points to a memory location on your GPU where you store the velocities. So that's part of the data I'm interested in. Um, I'll actually get to it when I write the main, but it's a parameter that you can define yourself. You can make as many as you want. Yeah, good. So then we get to the main function. So, oh, we have 2048 particles. Actually, I don't remember how many particles it's per block then. So yeah, that's a nice thing about CUDA. It just takes that number for you and it's all done for you. And then I have the coefficient, damping, the number of iterations I want to run my simulations for, and the number of iterations I want to spend inside of the GPU. I don't want one iteration per kernel call because that's inefficient. I want the kernel to do as much as possible, but I still want the intermediate results, so I still need to go back to the host program every once in a while to get the results. Otherwise, I cannot make nice animations. Then we allocate the memory. This is the random number generator. It generates a number between -10 and 10. Then I initialize the particles. They get random positions between -10 and 10 inside of a cube. Then I synchronize. So the data from the host that's stored in particles and that's stored in velocities has been sent towards the GPU. So now we're ready to execute the kernel. But like I mentioned before, we also want to know the size of the blocks. So we know how many particles we can store per block on the GPU. And CUDA device get attributed does that for you. Then we run the then we run the kernel. So I think the block size on my GPU was 512. Um, but it doesn't matter because the program will take care of it for you. So from that I can calculate how many blocks I need because there's so many particles that can fit in a block and I have so many particles, so how many blocks do I need? And from that I can also calculate what my shared memory size should be. So I have output code here. I request so many bytes of shared memory. These are block size and so many blocks I will have. The first write particles writes the initial positions of all the initial positions of all the particles. So that's my initial state. And then I loop over the number of iterations divided by the iterations per write. So if I scroll up a bit where I defined that, I want 16,000 iterations in total. Every GPU kernel call will do 20 iterations. So I would need to loop over 16,000 divided by 20 to get to 16,000 iterations. So I call my kernel, numblocks, block size, and here I have my shared memory size. So that tells the kernel that I want to use shared memory, and it should be that big. And then I have all my arguments, so num-particles, iterations per write, coefficient, damping, and these are memory locations that have been sent to uh, the GPU. So that answers your question. What's the parameter velocities? It's the memory location that contains the positions of the particles and the velocities of the particles. And then I have CUDA device synchronize, so it waits until the kernel is done before it continues the program. And then it writes the particles to the file. And then it loops again to the next iteration. So it does the next 20 iterations, next 20 iterations, next 20 iterations, etc. And then we're done with the program. And then we free the memory associated. Um, then we free the memory on the GPU. Then we free the memory on the GPU and the CPU because this is shared memory. So it's managed memory. So CUDA will take care of all of that for you. So then we're at the end of our program. And we've done 16,000 iterations for 2048 particles. And if I go back to my terminal, I have my code CUDA and body. That's right here. And I need to compile that. So nvcc, and my program is called nbody.cu. And I want to call it nbody as executable. and it's done compiling. And you can see we have the n-body program right there. And then I can run it. Oops, n-body. I keep trying to write nobody. And now it's running the code on the GPU. You can see I'm requesting 12,000 bytes of shared memory, and my block size is actually 1024, so I'm only using 2 blocks because I only have 2048 particles. Let's scroll down a bit to see where it's at. So yeah, you can see it goes pretty fast. Okay, so then I did the simulation before, so these are all the output files that it has generated. It generates a file for each iteration, for each 20 iteration. So every time the kernel function returns, it makes a new file called particle and then the number. And then when you look at that, it's X, Y, Z, and the velocities. It's all stored in CSV files. Oh, and it's already done. So I can actually open that. So pair view is a program for visualization. It's a very nice program. It lets you look at the data. I have the files in this directory. Open. Get rid of that. Center it. So yeah, this is the output. This is the final state of all my particles. And if I move back in time to the beginning, you can see it was a cube in the beginning. And if I run it, I think it goes very fast, but yeah. And this looks like there's some residual velocity. It's probably due to rounding errors. Not sure what else it would be. But yeah, that's how you write a program for CUDA and how to optimize for shared memory. So if we go back to the presentation, fortunately, there are many operations that are already done for you. So what I've shown you now is how to do the most basic. So you really go down to the core. And if you want to do a particle simulations like I have, you will need to write something like that. But if you want to solve matrices, um, there are CUDA libraries called CU BLAS, which does linear algebra for you. There's also CU sparse, which can do linear algebra for you, but with sparse matrices. So those are matrices that have a lot of zeros in them. You can also get a very efficient random number generator that's very good random numbers. The solver, which is a combination of the BLAS package, and it lets you solve linear systems of equations. There's also CUFFT, which is for fast Fourier transforms. Um, that's very nice, by the way. They're really fast. You can also do image compression because, well, it's still a graphics card after all. And there are also libraries for signal processing. I'm not too familiar with signal processing, but just want you to know that it's there. And of course, there are tensor calculations because, as you know, GPUs are used a lot in machine learning. Just because it's so many small operations on large chunks of data. The full list of these libraries is available at CUDA libraries on the NVIDIA website. So if you think about writing a GPU program, I would first check the libraries because that would have a lot of work done for you. Then there is the matter of where to run this, because you might have a GPU on your own computer or you might not. And even if you do, you might want to run multiple simulations at the same time. And if you only have one GPU, you can only run one simulation at the same time. Well, you can only run one efficiently, I should say. You can start the programs multiple times. But yeah, Compute Canada, it's something that's available for all Canadian researchers. And they really have hundreds and hundreds of GPUs. The most recent addition is the one called Beluga. They have 800 GPUs on them, close to anyway, and they're all free to use. So you can log into there and you can start using it right away. You do need to have an account though. So if you go to ccdb.computecanada.ca and as your institution you use the CAC University of Ottawa, you can create an account, and then once you have an account you can log in and you can run your jobs right there. If you're a student or postdoc, you need to have your supervisor create an account first. I see a question. We use CU Tensor for hardware acceleration for AI routines. Yeah, you can. What's more likely is that you would use an AI package already, like TensorFlow or um, Keras, which is part of TensorFlow. What's the other one? PyTorch. They will be using the GPU for you. So the CU tensor package is more for the in-between states where you create your own AI and you don't use TensorFlow or um, PyTorch, and you want to do the tensor calculations yourself. Then you would use CU tensor. Yep. Okay. So how to run? There's two wiki links that have all the information you would need for running CUDA programs and how to submit them to a cluster. You can also contact me, of course, because I'll help you with it. And ComputeCam is also nice because it can be used for developing code. Because like I mentioned in the beginning, CUDA, for using CUDA, developing a CUDA, you need a GPU. So if you don't have an NVIDIA GPU on your computer, you can log into ComputeCam and you can develop your code there. And the only thing you need to do is you log in, you type module load CUDA, and then the compiler is available to you. So you can compile your code with NVCC, like I mentioned before. And if you want to test your code on an actual compute cluster, you can use that command that I have here. So salloc time. So the time tells you I want it for half an hour, one CPU, 4 gigabytes of memory, and one GPU. You can also get code that runs on multiple GPUs, but that's a whole different topic. And then you run it with some name, and you can test your code for half an hour or however much time you put in here. And there's another platform. It's called Saskip. It's also available for Canadian research, but for this one, you need to write a proposal. So it's not a matter of simply creating an account and you have access to it. This is meant for academic industrial collaborations. So if you have a big project that requires a big simulation that could benefit from GPUs, or actually CPUs, because Saskip and Compute Can, you can use CPUs as well as GPUs. So they're really just platforms for massive calculations. So Saskip is more exclusive. So that means you have less waiting time. If you start your job, it goes right away. Whereas with Compute Can, you have to wait until there's space available because it's available for free for all Canadian researchers. So you can imagine that people like to use it. And there's more information in the link I put here in the slide. Then finally, I realized I gave a very brief overview on how to create a bare functioning, not barely function, a bare functioning program. But of course, you want to extend on that. The CUDA has really good documentation, like I mentioned before. So you go to docs.nvidia.com and you can get all these tutorials. It's all available for free, and you can learn how to do the more advanced things. The multi-tile algorithm I use is there too. They don't use it for particle simulations, they use it for something else, but I've forgotten what. There's also LinkedIn Learning. So if you are from U Ottawa, you have free access to it. So you can go to the link I have here, so LinkedIn Learning, and then this particular course is for Python, but the IDs are the same. So you load the Python module the Python package in Python, and then you can do the same things that we did in C++. If you're more interested in using OpenCL, so for instance, if you have an AMD card or you want to use it on Intel, it works on NVIDIA as well, then you can go to hands-on-opencl.github.io. They have some good tutorials there to go through all the things that you can do with OpenCL. And then finally, there is me. So if you need more assistance with Compute Canada or just programming in general to make your programs more efficient or make them run parallel, you can contact me. If you need servers installed in a data center or you want a virtual machine to host your website or whatever, you can contact me as well. So basically anything that is computational and is related to research, you can contact me for. So you can use our help desk, which is topdesk.uottawa.ca, or you can just email me directly and I'll help you out. And as a reminder, the code for this you can get at my Bitbucket. The code that I just showed you today is available on there, and I'll send out the slides afterwards, so you can look at them again because it's quite difficult to process, especially the bookkeeping, because you need to have memory on here, or you need memory there, and there's all these different memory architectures. So the best way to do it is just to take the code, go through it yourself, and try to run it yourself if you have an NVIDIA card or run it over Compute Canada and just try to make sense of it. And if you have any questions, really don't hesitate to call me. And I think that is my last slide. It is. So I'll just put my face on. So yeah, that's GPU programming in a nutshell. It's a difficult topic, but if you can get your program to run on the GPU, you can make it so much faster. So it might be worth it, depending on what you're trying to accomplish, of course. And yeah, are there any questions? Yeah, you're welcome. Yeah, you're welcome, Anmintor. You can also unmute yourself if you want and ask questions in audio, but you will be recorded. Yeah. Yeah, you're welcome, Kat and Kyle and Bing. Okay, so it looks like there are no questions. I'll make sure this recording gets posted on our IT website. In the meantime, I'll mail you the slides so you can get all the links that I've mentioned in the talk. And yeah, good luck with the GPO programming. And really, if you don't have any, don't hesitate to contact me if you have any questions or if you want to do anything else that's related to computers. Great, thank you. Have a nice day.